I'd like to welcome everyone to our Google Cloud Next On Air session. My name is Ryan Lippert, Product Manager at Google Cloud, and I'm going to be joined by Daniel Lewis from Geotab. Now, Daniel's a Senior Data Scientist and Research Specialist for Geotab, a company which works in the telematics space. That is, instrumenting vehicles to learn how to optimize fleet maintenance, routes, costs, and even city infrastructure. Now, to give you an idea of how hard that can be, Daniel's previous life was implementing machine learning on brain images. So not exactly a brain surgeon, but more the person telling the brain surgeon what needs to happen. So kidding around aside, the theme of what we'll be rolling through is how Daniel and Geotab were able to use Google Cloud's analytic tools to make their analysis of their business run easier. Or in their words, don't sweat the big stuff, make it Google's problem. So let's take a look at the agenda for this session. We'll start by kicking things off with a brief overview of BigQuery. Then I'll pass things off to Daniel for the exciting piece of the conversation. And at the end, we'll bring things back around and ask Daniel a few follow-up questions about his work. So let's go ahead and get started with BigQuery, the real-time cloud-scale data warehouse. Now, when it comes to analytics, we've seen advancements across different types of databases, data lakes, data engineering tools, business intelligence, and more. But the reality is that the data warehouse still forms the foundation for analytics programs across most businesses. This is important to recognize because it highlights the need to bring users new capabilities, not just through new tools, but through new features in their existing tools, particularly the data warehouse. Now, when we think of BigQuery, it's helpful to compare and contrast it with the traditional EDW environments. And those were traditionally complicated to get data into, restricted to only a few users, optimized for old-fashioned business intelligence, optimized for batch data. They were in need of constant patching, and you needed quite a few administrators for the operational tasks. Now, when you hear from Daniel shortly, you'll immediately know that this kind of tech wasn't going to work for Geotab. Now, when we look at BigQuery, it comes at this space from a very different perspective. We automate delivery into the data warehouse. We make insights accessible through the ability to scale out that data warehouse. We enable ML and AI from within the data warehouse. And BigQuery can do this all in real time while protecting your data and simplifying operations. So when you bring this all together, it has a dramatic impact on your business. And that dramatic impact is just how much time you're able to spend generating analysis and insights. When Daniel talks about not sweating the big stuff, it's a lot of what you see in this gray area from traditional data warehouses. Difficult, people-intensive processes that are about technology and not about insights. Now, from Google Cloud's perspective, we think the hard part is the applied analysis and the insights our customers, like Geotab, are generating. We're happy to handle the back-end technology part and let customers focus on analyzing the specific domains that they know like nobody else. Now, before I pass things off to Daniel, I'd like to quickly highlight a unique feature of BigQuery that, when combined with BigQuery ML, helps make some of Geotab's analysis possible, and that's BigQuery GIS. Now, many people know Google's long been an innovator and a leader in geodata, with more than 1 billion people using Google Maps each month. With BigQuery GIS, Google Cloud makes it possible to do core GIS functions directly in BigQuery with familiar SQL statements. So with that, I finished off serving up the appetizer for this session, and we can move on to the main course that everyone's been waiting for. I'm going to pass things off to Daniel, who's going to take you through how he and Geotab have put Google's technology to work in building out an impressive business.
Thanks, Ryan. So at Geotab, we make Internet of Things devices, these little hardware devices that plug into the OBD2 port of vehicles to enable smart telematics solutions. When I'm talking about telematics solutions, generally that's for fleets. And these little devices are used to track those vehicles and help companies make better decisions for managing their individual vehicles and ultimately operational efficiencies across their entire fleet. So we've got a pretty small data science team at Geotab, though it's grown significantly in the last couple of years, but we're able to do so much for our customers because we can rely on Google to handle all of the big back-end stuff and allow us to really focus on spending time to solve our customers' business problems and our own internal business problems. So today we're going to talk about going from all of those individual telematics devices and kind of the customer level to how you can bubble that up using Google's awesome scalable back-end tools to produce globally scalable analytics, leveraging the whole Google Cloud ecosystem of tools. So as of today, we've got devices installed in more than 2 million vehicles around the world. And as I'm talking, you can look at this really beautiful map in the background, which shows just a single day of vehicle coverage in North America from our connected devices. So these devices are constantly streaming data back about the vehicle's position, its speed, its acceleration, the RPMs, engine status information, coolant temperature, oil temperature, fault codes. There's an onboard accelerometer. We're going to be adding a gyroscope and just tons of information constantly streaming back. Now, server side, this results in over 40 billion data points per day, which is just terabytes of information on our end, just constantly streaming. So managing that streaming process alone, that's already a huge scalability challenge. It's one that we solved with Google's tools, among many other problems that we've encountered. But due to time limitations, today we're just going to focus on what we do after we get all of that data, which is where my job really comes in and the part that I get really excited about and find really interesting. So what do we actually do with all of this data, these 40 billion data points that we're getting every single day? So 40 billion data points is really great. It's awesome. I love working with that amount of data, but just the data sitting there is not actionable in any way for anybody. No human can go in and just you look through that information and try to parse it and get anything actionable out of it just by looking at it. So what we want to provide to our customers are things like solutions, something that actually solves a business problem using that data. We do a lot of things focused around a few different key areas. Some of them that are really interesting for our fleet customers are predictive maintenance solutions, preventing breakdowns before they happen, predicting battery failures, that kind of thing. These roadside breakdowns are very expensive. We want to use all this data that's coming off the engine to prevent that from happening. We do things like artificial intelligence-driven smarter fleet management. And today's focus is going to be more on kind of the broader network scale things. So smart city analytics and solutions to make kind of less congested and just generally more efficient cities around the world, which is a win-win for everybody involved. So why do we care about congestion? It's a really big problem. If you're looking at just North America, congestion caused urban Americans, so not even all of America, just urban regions, to travel an extra 8.8 billion hours. This was in 2019 for a congestion cost of $166 billion. So it's a bit of a problem. These are just numbers for America. It's an even bigger problem globally. So we definitely want to do something to solve this or make it a little bit better if we can. Now there's 20,000 cities in America. So most of those are really small, but it's still a lot of cities, and there are multitudes more around the world. So it seems maybe a little bit intractable to start thinking about how we can optimize infrastructure across 20,000, 30,000, 100,000 cities. But little small improvements really do matter. They can scale. You can make these little bitty changes, and across hundreds of thousands of individuals, you can wind up with really big cumulative impacts. So just an example in San Francisco, I looked up the numbers there, and we've got a few 100,000 people entering in cars in San Francisco every single day, on their way to work. And if they have to stop at only 5 individual intersections in the city, and we're somehow able to shave 3 seconds off their average stop time, we're going to save 375 hours of idling every single day, giving each commuter an hour of their life back. This is great for the commuter. It's great for the city, getting more people through, less congestion, less impacts on the environment. It's a win-win for everybody involved. In order to improve anything, though, we need to know what the current reality is. We need to know what the current state is so that we can push forward in a direction that we want to improve in. We have to start with data, and we have to start with a lot of it, as you saw from our previous slide. So here's an example of the type of thing that we might want to produce for a city. So on the left there, you can see a heat map of downtown San Francisco, and the heat map is just colored by the average wait time in seconds for a given hour of the day in the city. Now imagine that you could just zoom into any city in the world and access this kind of detailed information for every single intersection in that city without any kind of infrastructure changes. No camera installation, no strips to lay down, no trenches to dig and put strips in, no one standing at the corner with a clipboard and stopwatch, which in talking to cities, amazingly, this still happens. Imagine you could just get all of this information instantly from all of the cars that are already driving around. You don't have to do anything. This is really what we're trying to achieve, and this is what you can do when you leverage Google Cloud because of the volumes of information that we're able to handle with that backend. So to achieve this goal in this particular talk here, we're going to restrict the scope a little bit to something a little bit more manageable, and that's going to be focusing on signal-controlled intersections. So these are the things that the city can tweak immediately to get some short-term feedback on impacts and iteratively move towards a better solution. So this is the kind of thing that we're thinking about when we're talking about traffic light optimizations. Going in and removing a stop sign or adding a stop sign or adding or removing lanes, adding dedicated right turn lanes, coming up with diamond interchanges, these kind of things, total infrastructure changes are things that you definitely have to consider, and they have large impacts on traffic congestion, but they're not something that can be easily or cheaply manipulated or changed. With traffic signals, you can make improvements with just the lights though. If we're looking at something simple like a north-south or east-west direction intersection like we've got here, how much green do you allocate to each direction? That's an optimization problem. If you've got 70 second, 140 second, whatever it is, light cycle time, there's only a certain amount of green that can be allocated in either direction. If you give it more in one direction, it has to be taken from the other direction. And that has impacts upstream and downstream. So how do you actually know what's better? And is the problem at this intersection, or is it upstream or downstream of this intersection? On a particular day, is it because of the normal cyclical traffic flows, or is it because of an accident, et cetera? We need a lot of data to be able to determine what the optimal light timing actually is for any given intersection and what the impacts would be on the network if we were to change it. So that's the type of question that we're trying to answer with our data. However, streaming a lot of data is very, very expensive. So it's getting cheaper all the time. And when you're talking about millions of vehicles constantly streaming data, those little bits of cost add up pretty quickly. We can't do continuous data sampling. We've got real devices, real hardware limitations, with local storage limitations as well, real data transfer costs. We need to figure out what the ideal sample rate is. So what's the ideal sample rate so that you don't miss, for example, going around corners? As you go around a corner, there's a lot of different things happening. We don't want to miss the corner, et cetera. So you need a higher sample frequency than if you're just going in a straight line down a freeway, for example. If we were to constantly drop points, every 10th of a second or something, we're bringing back a lot of redundant information because we know you're just going in a straight line down the highway. If you have a uniform sample rate, you can't really solve both of those problems simultaneously. If you crank up the sample rate such that you're catching those corners, you're going to be sending back way more information that you need in areas that you don't actually need it. We solve this at Geotab with something called curve logic. It's kind of a simple but very elegant idea that we use to minimize the data transfer costs. We've got a couple patents on it listed there. And the basic idea is really simple. You can watch the cool animation there on the right while I describe it. But essentially, you just have a high frequency sampling on the actual hardware device. And then that's stored in a local storage buffer. Before you send that back, you go through that buffer and you choose points from the sequence of high frequency sampled points such that linearly interpolating between them, which is what you kind of see with these red dots there, no intervening dropped point would be more than some chosen error threshold away from the line. And that's just a parameter that you can tweak depending on your use case. And then from the device to the server, only sending back those individual points where we were linearly interpolating between. So only those red points get sent back to the server. So we use this technique to really efficiently send the minimal amount of data back to our servers that enables accurate trip reconstruction. So when you're going in a straight line down the highway, we may only need to drop down 1 or 2 points from your initial point in order to tell that you're still on that highway. And then when you go on the off-ramp, we're going to drop a whole bunch of points and send those back to the server to make sure that we didn't miss your turn off that off-ramp. Now, when we do this, we come back and we start looking at the data in BigQuery and on our visualizer tools and that kind of thing. The first obvious thing that's going to happen is now we've got gaps. So on the server side, we have all these gaps. We know in reality, you would have had to have driven through that little green circle, that intersection there, in order to get from one side of Fulton Street to the other side of Fulton Street. So how are we going to fill in all of these gaps server side? We know that because we did the curve logic, that linearly interpolating between those 2 points, we would have never been more than the error threshold that we chose away from those. So we've got our 2 million vehicles generating billions of points. We know that in order to fill them in, we can just linearly interpolate between them. But with 2 million vehicles, billions of points, how are we going to actually do that in a scalable way? We don't want to just linearly interpolate necessarily at a huge resolution in areas we don't need it again, but we want to make sure we don't miss the intersections. In our particular use case, because we are focused on high quality data reproduction for these intersections, we're going to drop them at a scale that allows us to ensure that we've got coverage in every single geohash of interest, which I'll get to later to do efficient spatial joins. In our case, that's a little bit under 9 meters. So we've got 2 million vehicles, 40 billion points a day. We have to fill in all of these gaps at a resolution of 9 meters. As you can imagine, that's a really difficult process involving connecting tons of different systems, trying to scale out and parallelize the interpolation, et cetera. Nope, not at all. Just kidding about that. With Google, you don't need to sweat that big stuff. End to end, we never leave the Google ecosystem for this project. We just make the big stuff Google's problem entirely. Let them handle the hard back-end work. So as you can see on the slide there, with the details on the right, we run a daily interpolation for all of our vehicles, and this actually runs in less than 20 minutes. All you have to do is work in a little bit of the simple math. We're doing linearly interpolated point dropping between our GPS points, and Google worries about scaling all that out on the back end in a parallelizable way. We never have to leave BigQuery. It's really, really, really simple. So we've been able to minimize our data transfer costs and accurately reconstruct the trips on the server side. Now, the reason that we're able to do all of this super efficiently is because of the tools that Google has been continually innovating. And one of the things that Ryan mentioned at the beginning was BQ-GIS. This was really a game changer for us and enabling us to do all of this scaling. So July 2018, if I remember correctly, is when BigQuery released native geospatial support. This allowed us to move away from relying on JavaScript UDFs. So those were really powerful at the time when we were using them, but they don't scale out as well on the back end as kind of native BigQuery functions. So when we started switching all of that over to BQ-GIS functions, we were able to really balloon the scope that we were looking at for this type of things. So before we were running it on a region to region basis, and now we run this every single day for the entire world. We're constantly leveraging BQ-GIS functions and weaving them into everything that we do. So we've got all of our data back from the vehicles. We've reconstructed these trips and interpolated the points. We've got all of the locations at a very high spatial resolution. So what do we actually want to do next? We have this data, but what we're trying to do is find these intersections so that we can track vehicles through them. Now, this is the tricky part. So for a proof of concept and for the purposes of this presentation, we used OpenStreetMap traffic signals as our point of reference to look for intersections. So an intersection is not something that's actually generally well defined in a geometric sense in many mapping solutions, and particularly in OSM, there's a lot of possible configurations for traffic lights and ways to come into an intersection. You can see a sample of them here. Sometimes you've got 2 ways and 3 lights. Sometimes you've got 4 ways and 1 light, 8 ways and 4 lights. There's a lot of different configurations, and there's no real concept of like the intersection itself, or if you imagine kind of like the polygon that would wrap around the roads that lead into that intersection. And it's not so easy then to map these kind of individual ways and connected nodes and lights to something that has like geographic representation of what the intersection actually is in terms of what a human would understand in terms of behavior of cars through it. So how do we go from some number of traffic lights and some number of ways to kind of a single point and its associated geometry to represent that intersection? And the way that we solve that is just start with a really simple algorithm, dbScan. So we're going to leverage the dbScan algorithm, which is really simple. It's a really powerful algorithm. It's been used for decades, and it's really great at finding local clusters of points. However, even for this really simple use case, it really quickly becomes a scalability problem. So if we're looking at the whole world, OSM has about 1.2 million traffic light nodes. This leads us to 742 billion pairwise combinations of distances. So if you had data storage in a 64-bit NumPy array, that's more than 5.5 terabytes of RAM already needed just to store the distance matrix before you started doing any calculations. So on top of that, dbScan is not a really easy algorithm to parallelize. So, I'm starting to sweat a bit. This doesn't really seem tractable. How are we going to do this? There must be some way that we can make this Google's problem, and there definitely is. So we can solve this actually pretty easily with Dataflow. Dataflow is great at handling this kind of stuff in the back end. So let's utilize some of the information that we have about the connectivity of these lights. We're not going in blind here. So we know that some of them are in certain ways, those ways are connected to other ways, and those ways have lights on them, some of them don't, etc. So we know something about the relationship between the nodes and the ways and how they're connected in the street network. So what we're going to do is we're going to utilize those connectivity relationships to reduce the search space around each light, where it's only calculating distances to lights that are within some number of connectivity hops to the light itself, plus some other connectivity parameters that we introduce, such as the type of road and street names, that type of thing. So these are all hyperparameters that we can tune in our approach. But assume that we've done that, and this leads us to a markedly reduced number of preclusters. And with those preclusters, we can then run a parallelized dbScan. So when we do this approach, we get about 1.6 million preclusters to perform dbScan on. Each of those are independent of each other, though. So this means that we can now parallelize it. And on average, they have 9 points or less, which is a much more tractable problem for dbScan. It's a much smaller pairwise distance matrix. So we can basically just throw this at Dataflow now and let it handle all the hard work of parallelizing this across all these 1.6 million clusters on the back end. Let it scale up the machines, let it worry about how to distribute the work, how to collect it after, and how to stream it back into BigQuery. All I had to do is figure out the approach. So we're able to really easily do this, and this runs pretty fast. So now we've identified 700,000 intersections in the entire world in less than 10 minutes using just BigQuery and Dataflow. So this is excellent. We still haven't left the core Google Cloud product suite. So now we can go on to the next step, which is mapping the roads. So once we have the intersections, we have to accurately map the roads in order to accurately track where the vehicles are actually coming from and going to, so that we can get accurate metrics at a per intersection level and ultimately chain them together to get quarter analytics and kind of like the broader network effects as well. So in order to efficiently generate these trips, we want to be able to do a very simple geospatial join. So if we were to do something like a simple naive cross join between all of our GPS points and all of the roads in the world, and maybe use something like a BQ-GIS function like std within, we'd have an absolutely astronomical number of rows. So this is not possible even for Google yet. It's far more than BigQuery can handle. So there has to be a better, smarter way that we can figure out what road you're on really quickly in a scalable way for these millions and millions of vehicles and these billions of points. And there's a lot of smarter ways that we could do this. And at Geotab, we tend to use geohash for geocoding latitude and longitude. So geohash is just a Z-order space filling curve. You can think of it, if you haven't used it before, as something just like nested rectangles that cover the whole globe. And any latitude and longitude pair inside one of these little rectangular boxes gets assigned a string, which is unique to that box. And there's a lot of other mapping systems such as S2 cells, H3 cells, etc. But at Geotab, we tend to use geohash, and it has native support in BQ-GIS, which is great. We don't have to jump out to JavaScript UDFs. So this allows us to forget about the impossibility of accurately joining floats and the impossibility of doing these cross joins, enables us to do a very fast straight string join based on geohash. So that's great, but that then leads us into another problem. So if we're going to be doing the straight join on geohash, we have to then know which geohashes are actually part of the road network and which parts of the road network are associated with which intersection. So there are some machine learning approaches that we've used, but there are actually some simpler, cleverer ways that you can do, leveraging the ability of BigQuery to scale really efficiently before you even have to get into the machine learning area. So the hard part, back to the problem, which is really a trip generation problem. In order to generate trips, again, we need to know what the set of possible traversals is through any given intersection to segment the vehicle path into intersection-based trips. So before we even think about associating the geohashes with the ways, we need to know which ways are associated with the intersection. So as a first step, we can just pull all of the directly connected ways out of the intersection, so anything that's directly touching or connected to a traffic light. So you can see an example of that on the bottom right of the slide. For some random intersection that I just picked. However, you can already see on the map, the adjacent intersections to the left, right, north, and south are further away than those ways that are extending. So we've got these directly connected ways, but they don't actually map all the way to the next intersection. So if you were to just base trips on this, they're not actually going to be accurately reflecting the metrics for those vehicles. We're only going to be counting vehicles that are on those lines, assuming we've done the geohash associated with those lines. So we miss all of the intervening information from when you left the previous intersection until you get to these short distance approaches here. So that's something we're going to have to fix. So what we actually need to do is start with all of those directly connected ways and then somehow get all the ways connected to those, and then all the ways connected to those, and so on and so forth, going backwards until we either run out of ways that are connected or we hit the next intersection, while simultaneously somehow taking care not to include side streets and different types of roads and things like that. So you can see with the code on the bottom right there, it's actually pretty easy to get all the connected ways. It's a really simple join on the nodes. There's nothing really challenging about that. So this is ultimately what we want to do. You can see there's 132 connected ways here. So we've got our simple query to join back and get the connected ways. In this particular case, we know how many there are, so we're good to go, right? We just keep joining until we've got all these ways that are highlighted here for this intersection. But of course, it's never quite that easy. So we don't know a priori for any given intersection how many ways are connected, so we don't know how many times we need to actually join. So what we're going to have to do is look recursively until we run out of connections. And in order to scale, we know we want to do this recursion in BigQuery and just leverage SQL. Unfortunately, you can't do recursion in SQL, so what are we going to do? Or can we? So I was super excited about this, and it's really recent. So in November 2019, BigQuery released native scripting support, which is really amazing and powerful. It allows you to do really quick prototyping, experimenting, and iteration of things that weren't really possible before right inside BigQuery and right inside the UI. So you can run scripts via API, just like a run-of-the-mill SQL query. You can run it in the UI. It's got all the basic building blocks as well that you would want in a scripting language, like conditional execution, loops. We can mix DML and SQL, and it gives us some really powerful capabilities. And we're going to leverage all those capabilities to solve this connectivity problem. So I was really excited when this came out, and I immediately ran over to the documentation. And unfortunately, the documentation for this is super underwhelming, and they actually are really underselling the power and capability of this tool. So if you see on the left there, that's like the example for loops in the documentation. No one would ever use SQL to increment some random variable X and spit it out at the end of the loop. This is just not a use case that would happen. This is really the extent of the documentation that they have for loops. So I wanted to do something a little more fun to learn it, and then also showcase the power of it. So I went and tried to implement a recursive Fibonacci generator using nothing but SQL and BigQuery, and the result is here on the left. It totally works. I wouldn't recommend doing recursive Fibonacci in general, and definitely don't do it in SQL. But the point is that this is a really powerful tool, and things that you would think are not going to be possible to implement in SQL and weren't before, you can now do really easily in BigQuery. And you can copy the code there on the left if you want and run it. It totally works. It's going to hit scaling problems at some point as it kind of explodes recursively, but the point is that it works. And when we implement this in a smarter way, we can solve things like our connected ways problem without ever leaving the SQL environment and letting Google handle all that big, complicated backend stuff. So here's some actually usable code. So on the left there is the final code that I wrote to actually do this with a SQL scripting approach. So what we can do is we can build a while loop that just keeps joining backwards and keeps joining backwards on way nodes until we can't find anymore. So it's a really simple while loop. We can set some break condition if we want, 15, 30, 100, whatever we like in terms of number of connected hops, and insert the results of each step into a reference table at the end of a loop iteration. And at the start of the loop, we just join back on it with the ways and nodes in the next loop iteration. And we just keep doing this, and we just keep doing this until we hit our break limit or until the table size stops changing and we know that we've run out of connected ways. So once you bring in the ability to leverage loops, this actually becomes a really simple problem to solve. We just take our simple join and we recursively iterate until we run out of connectivity. And then you can just lean on BigQuery and its awesome ability to scale. And this whole thing actually runs in less than an hour for the entire world. So Google handles the parallelization on the back end really, really well. So here's like the results of that in a particular neighborhood. This is just Oakville, where I live. And this has been done for the entire world. So we've got every single connected way associated with every single intersection in the world So this is really fantastic. And in combination with the data flow step that we did before and a couple of BigQuery step, we're still under 2 hours end to end to do all of this, to get all the connected ways associated with intersections for the entire planet. So what do we actually do with it? So we have the roads, but this doesn't actually solve the problem yet. We still need all of those associated geohashes, and we're back to our original cross-join problem. Except instead of geographic points, we now have geohashes. So we still can't just join these geohashes on the roads, the geohashes that cover the whole planet, and figure out which road they're on. So we've still got 20 billion geohashes and 18 million ways after these reduction step. That's still a 386 quintillion row cross join. That's still way too much for BigQuery to handle. So again, we need to come up with a smarter, clever, more clever way to do this. Now, Google's really good at scaling, which is the point I'm trying to drive home in this presentation. So if you can craft a problem in such a way that the hard part is scaling, at least within astronomical limits, you pretty much won, because Google can just handle all that for you. So let's do that. So let's think a little bit more carefully about the problem and create it in such a way that we're stuck on a scaling problem, and then just throw it at Google and let it deal with that for us. So what we can do is actually break this problem down into 2 primary steps. First, what we need is actually a subset of close by geohashes. From there, we can restrict this set of geohashes in some way to those that just cover the road. And then we are back to our original problem where we have our interpolated GPS points. And because we can easily get geohashes for those points directly with BQ-GIS, it's just a straight join, no cross join required anymore. And now we've got something that's going to work really well, and it's going to scale really well. So we can't just geohash the nodes that make up the ways. Those are unevenly spaced on the road, so we're going to get gaps. We could start with that maybe and look at like parent nodes, neighbor nodes, parent neighbor geohashes, etc. But we're going to have a lot of edge cases to deal with there. And those arrays kind of don't scale super well. We know that cross joins aren't going to work. So how are we going to actually do this? So what we need to do is make some sort of search space ourselves. We can do this using just SQL UDFs and BQ-GIS again. So all we really need to start with is some reduced search space, which we can visualize as a bounding box with some incremental spacing from one side of the bounding box to another. This gives us basically a matrix of possibilities of lat long points that we've kind of stepped through. And we're going to convert each of those into a geohash using BQ-GIS, and then only retain those geohashes that are within some distance of the road. We can let Google then handle the big stuff, which is scaling out this approach to the entire world. So this is the result of our first pass on a randomly selected road. What we've done is surrounded this particular road with a bounding box, which you can see on the left there. It's very easy to do just by getting the extents of the geometry and adding some buffer space. And then we have this kind of wrapped box around the road. And then we simply use BigQuery to generate an array where we step by an amount smaller than the geohash dimensions of interest, kind of taking into account the distance from the equator because they're not perfectly linear. The Earth is not flat. And then we geocode these points of lat long into our grid of geohashes. And then voila, we've covered the whole road with geohashes. So from there, we can now finally do our STD within function that we were talking about several slides ago. That's just a singular geometry comparison for each way and its potentially associated geohashes instead of this massive cross join, which isn't possible. So now we've done this STD within function, and we've got all of the geohashes that are covering the road. We get the estimated road width based on things like the number of lanes, the geographical region of interest, the prescribed kind of maximum minimum road widths for a given municipality, etc. And we've got some models that do that. And now we've got a wonderfully reduced set of geohashes that accurately covers the road itself. So once we parallelize this a few times with modby, this actually runs in less than 4 hours for the entire planet. So here's an example of just all of the intersection roads in Singapore for fun. And so remember that we never left BigQuery for any of this. I never looked at any data from Singapore. I picked a few local examples, figured out how to best kind of cleverly come up with a process that leverages the ability of BigQuery to scale. And then we're going from basically a text string representing the geography of a roadway, which is stored in BigQuery without any direct relationship to the intersection, to a set of all of the geohashes covering all of the roads in the entire world that lead up into a particular intersection using nothing but SQL. And we still spent for this whole pipeline only around 6 hours from end to end to run. So all in a day's work, we've gone from some simple text strings to representative geohashes covering the entire planet. So now we can actually go and start generating metrics for the cities. And this was the purpose of kind of doing all of this to begin with. So since we have intersections with labels and all of their associated geohashes now, their centers, their bounds, etc., all we have to do is geocode our vehicle path GPS points into geohashes and then join back on this intersections table that we've created. From there, we can easily assign each portion of a trip to the intersection that it passes through next. And from there, it's a simple matter of tracking things like speed, the number of stops, the idle time per stop, the total distance traveled, the point from which you first stop, which we can use to infer queue lengths and things like that, to pull out really any metric of interest and subsequently aggregate up to the time period of interest. So if you imagine you're traveling out of your driveway and you get onto the road, And at some point on that road, you're going to hit an intersection where you have to make a turn decision or a straight through decision. So the point from which you leave that driveway to the point which you get to that intersection is going to be one subset of your total trip. That subset has a bunch of metrics associated with it and get associated with that intersection that you then pass through. From the moment that you leave that intersection, we start counting again towards the next intersection that you experience, and so on and so forth. Then we break up all of your driving into these little trip segments that are associated with a given intersection. And an example there on the right there is just for the region of Toronto. So using that aggregated information, we can now really easily generate all sorts of insights for any city where we've got vehicles. And as you saw in one of our first slides there, that's pretty much any city in North America, and we're expanding globally as well. So you can see some cool examples on the slide here. So on the left, we've got the average trip volume for heavy duty vehicles. You can see that they tend to prefer certain corridors through the city, and this is the Las Vegas region. On the top right for Las Vegas as well, we've got a corridor analysis heat map of individual trips through a sequence of intersection. And this essentially shows you the propensity to have to stop at any given intersection along the corridor. On the bottom right is just a simple heat map example showing the percentage of vehicles that have to stop at any given intersection based on the turn direction. If you look closely, you can see some interesting patterns there, like rush hour times, depending on the direction at certain times of day, around 8 a.m. and around 5 and 6 p.m. And at the bottom there, you can actually see two right turns, one of which has a significantly higher propensity to stop than the other one. And if you go and look on the map, it's because that turn direction has a dedicated right turn lane, and the other one doesn't. So the one where you don't have to stop has a dedicated turn lane. And little things like that are really easy to pick out of these things and really validate the infrastructure changes that you've been making. And then with this kind of information, we can roll it up to any time period of interest. So you could do, for example, a few week period before a light change the light timing, and then look at a few week period after and measure if there were any differences. And doing this throughout the entire city and looking at the network effects upstream and downstream, you can really start to optimize and shave off those few seconds that we were talking about that gives people back, time and money of their day, and really helps reduce the environmental impact of idling and congestion. So that ends kind of the tech portion of our talk here, and I wanted to jump into a Q&A with Ryan. So he's kind of scripted some questions that he didn't really share with me beforehand. We wanted to do a sort of live Q&A to give you the feel of actually being with us here as an audience.
Hey, thanks, Daniel, and thanks so much for sharing everything there. The stuff that you and Geotab are doing is really impressive. And I think, as you mentioned, it was a little bit more on the technical side, by design, the conversation that you just had there with the listeners. Can you talk a little bit more about what the benefits are on the business side for your customers and how that works?
Yeah, absolutely. There's this impacts of this particular project that we worked on, and we do a lot of other things as well. But I'd also just say that a lot of our customers actually are cities and have their municipal vehicles hooked up with our IoT device. So that being said, though, there's a lot of impacts for our fleet customers as well from something like this. So if you're a heavy duty vehicle driving around the city, every time you have to stop, that idling uses up fuel. It also takes a lot longer for a heavy duty vehicle to accelerate again. That uses up fuel and driver time and things like that. And then from the city's perspective, when that big truck has to stop and then accelerate again, that causes congestion. So it's a win for the city by reducing congestion, reducing emissions, idling, things like that. But it's also just a win for our customers and having to spend less gas and waiting less time. And when you think about one individual truck, it maybe doesn't seem that big of a deal. But if you think back to the San Francisco example with 450,000 cars, so most of our customers don't have that many, but some of them definitely do have 5, 10, 20,000 vehicles. If you imagine these little stops constantly across all of these cities, when you've got 10, 20,000 trucks driving every single day, these little improvements, they really add up if you can make those small changes. And then speaking with certain cities, so you saw on the map before with Las Vegas, there are some corridors that trucks like to travel down. And a city, once they have this kind of information, can start to think about things like freight signal prioritization. So because these trucks take a lot longer to accelerate, there's a larger congestion impact from them having to stop. So if you're a city wanting to prioritize freight along a certain corridor and minimize the congestion impact, you can do things like give it an extra couple of seconds of green when a truck is approaching to let it go through. So obviously this is a win for the customer because they don't have to stop as much, and it's a win for the city not having to reduce congestion.
I don't think there's any of us who wouldn't rather have less congestion on the streets. And so I think that's a win for just about everyone out there. You mentioned that you're staying within Google Cloud as you do this, and it's BigQuery. There's some data flow in there. Can you help describe to our listeners out there what it would take if you didn't have BigQuery and the surrounding tools?
Yeah, absolutely. So I think a lot of it would be what you mentioned at the beginning. If we didn't have all of this amazing infrastructure on the back end to do the scaling and manage all that for us, we'd have to spend a lot more time in that gray area and actually managing and building out the infrastructure. And that's not really where data scientist skills or expertise lies, at least not for me. my expertise and my value add is in solving these business problems for people. And if I had to spend 80, 90% of my time building out the infrastructure, the end solution probably wouldn't be as good because I can't devote as much time to it. So what we probably would have done then is using the tools that we had, if we didn't have all this amazing ability to scale, just really reduce the scope down. We maybe would have had to do it neighborhood by neighborhood or maybe city by city and come up with other kind of limitations to restrict the amount of data that's going in, just because we wouldn't be able to handle it. But because we're able to do this globally, which helps us to be a much more powerful product.
Makes sense, Daniel. So, hey, as we wrap up, do you have any parting words for the listeners out there, advice on how to try out new features? I saw how fast you put scripting into production. I thought that was really great. Any tips for the listeners out there?
Yeah, absolutely. So I know I poked fun a bit at the documentation in the talk there, and some of it has some things I like to make fun of, but overall Google's documentation is actually really, really good. So when the new features come out, I dive into the documentation right away. I pull out the examples. I try to implement them. I try to implement them against my own data. So, everybody watching, you're experts in your own data. You know where your bottlenecks and your problems are. Think about ways that you can leverage these new tools that are coming out on your own data sets. And if you're not quite there yet, BigQuery's got a lot of sample data sets in there and you can play around with those, but really need to start digging in and applying it to actual problems to understand the new techniques, the new tools and their capabilities. And once you do, it's almost always the case that you can really quickly implement it in production and get some really big wins, like we did with BQ-GIS and like we did with SQL scripting as well. And Google's also got lots of great champions like Felipe and Lakshman that are constantly pushing out content about how to use these new tools with examples given. And if you can just go and replicate their work, start making tweaks, thinking about how to apply it to your own data, you can actually get ramped up pretty quickly with all of this stuff. That would be my advice.
Daniel, great advice to go along with a great presentation. Can't thank you enough for coming and sharing your thoughts today and what you're doing at Geotab, and just wish both you and Geotab the best of luck going forward.
Thanks, Ryan.